bit of time left. Let's use it efficiently. Everyone ready? Yes, yes. No. Running, I like that. Shows urgency. Dedication. It's required in operating systems. Good job. Good. We have some administrative stuff. Um, we have an exam coming next week. We'll go through Tuesday. We'll figure out somewhere in there where to do some review. And then the exam will be on Wednesday evening. That will be, there's 2 rooms assigned to us. It's probably written down on the webpage somewhere. We'll decide how that works, like for even versus odd student ID numbers, something like that. And it will be in person with, paper, so old school, no creepy camera in your, bedroom or whatever. I mean, what have you been subjected to? It's historic, right? What's been happening, what strangeness has been happening. Has everyone taken an exam with the creepy camera? No, some of you? How creepy is that? It's kind of creepy, right? Yeah, I don't like it. So anyway, we're just doing it old school, which means we're killing trees instead. There's a trade-off. So we'll kill some trees. It'll be great. You can look on the webpage, etc. Posted in Piazza. There's links to all the old exams. Feel free to look through those. It'll be something like those, but something different. You know how that goes. I haven't made the exam yet, so I can't tell you any. I intentionally wait a while to tell you about, not to make the exam rather, because if I make it too early, then you ask a question and then I can answer it only honestly, and there's a problem then. So I don't make it until late. Yeah. Yes, great. So other question is P2. So I didn't want to overwhelm everybody. I figure we're still just coming back from COVID, getting used to school, working, all that stuff. So I wanted to make sure that we'll introduce P2 on Thursday. It might be announced a little bit before then, but then you'll have, a bit of time till like the following, not Thursday to Monday, but Thursday to Monday to get P2 done, P2A. So you'll have some time there. I wanted you to have time to study for the first exam. How generous, I know. It warms your heart to think how much I care. Oh yes, let's clap. Yeah, yeah, yeah. I, I don't know. Maybe I'm just getting old, it's just whatever. It just felt like it was a little too mean to force you to do another project, then study for the exam, then, do whatever. I think you have other classes too, right? Something like that. So that'll come out in the next day or so. We'll go over it Thursday night, and then you'll have some time to work on it. Um, so that's project exam. Any other questions about the exam? Yeah. Do we have class on the Thursday after the exam Wednesday? I think you're asking me, can we skip class the Thursday after? I like how you're thinking. Let us let us consider that. Let us consider. We will think. Um, so maybe not. It would be nice not to have class, wouldn't it? Yeah, that would be nice. Okay. So we'll figure something out. Um, so that's that. Any other questions about things you want to skip? No? Okay. Yeah. Will it be multiple choice? I don't know. I haven't made it yet. I mean, there's a lot of you, which leans towards automatic grading, but I don't know. I really haven't made it. So I'll let you know when you take the exam. Yeah. What time is it? It's at 7:15 on Wednesday night. Is that bad? Isn't that the normal time? All right. I don't think I'm inventing anything here. That's the time. You come here, it's exciting, everyone's nervous, it's exciting. It's a lot of fun. I mean, it's a lot more fun for me than for you. But don't you get that fun, nervous energy when you take an exam? That's like kind of exciting, right? Like you test yourself. No? You should. I mean, if you have dread, that means you didn't study. That's all that means. Dread is you didn't study. If you study, you will 100% do fine. Like just literally look at the questions I ask and then like look at like homework, like just look and you'll find that they're very similar. Very similar. Often very similar. Not the same, but similar. If you can do the homeworky questions, if you can do the Canvas quiz type things, you'll be fine. Later you'll call me a liar, but that's different. That's after class is over, and then our relationship has ended at that point. So, um, Anyway, let's move on. Now we're starting to notice any other questions. Quick, administrative questions. Those are so fun. Yeah. Oh yeah, PM. Yeah, PM. Wednesday PM. 7:15 PM. That's evening. What should we do military time? It's 19:15. It's late in the day. Military time. All right. So very cool. In the evening. Yeah, that's what's fun. If it was in the morning, you'd all fail. I mean, I know that. It's hard to wake up early. Okay, good. Any last things? Okay, and we'll talk more about the exam. Don't worry about it. I mean, worry about it a little bit, like prepare for it, but you should have a time to prepare for it. Okay, so what we're getting into here is what we're noticing here is with a realistic address space size, we already have a problem. We have a lot of pages, and each one of them needs to be located somewhere in memory, and we have to track that somehow, right? So, first problem with paging is that there are too many pages, or it's a lot of pages is maybe what I should say, maybe not too many. So our example was, 2 to the 20th. And remember, this is per process. Each virtual address space has 2 to the 20th pages, right? There's 32-bit address space with 4K pages. Each one of them has roughly 1 million pages. And we might have to track some information about each of those. That's a lot of information per process. Right? It's a lot of information. So that's a lot of information. This is like the qualitative answer, which I was making fun of it earlier, and now I'm fully diving into. It's a lot of information per process. So the question becomes where to store this information. Now, previously, the translation information was right there in the, it was kind of like when we're using it, it's right there in the MMU, right? There's this like a few base registers, few bounds registers. But building an MMU that stores, 1 million translations, that's not going to be a very efficient structure. So the natural thing to do is actually going to be just to store this in main memory. We're going to store it in main memory. Each running process has a bunch of information related to it about translations. It's going to be stored in main memory and managed by the OS, right? So this is managed by the OS. And in fact, it's stored in a particular data structure, which is so well known that it has a generic name called a page table. Very exciting. Page table. We're going to talk a lot about page tables and how they're built in this class over the next few days. So there's it's just a data structure, and there's lots of different ways to build them, but we're going to think of them to begin with as this per process, there's a page table. The page table, inside of it, is going to store all the relevant virtual to physical page translations. Okay, so that's a ton of information. It's going to be in physical memory. And we'll talk about some issues. That's going to cause a problem too, but this is problem number 1. Too many pages. So let's think about what that means. So let's have our example here. Let's say we have a small address space just for simplicity. Let's have 8 pages in this one. So virtual page 0, 1, 2, 3, 4, 5, 6, and 7. Now that's a very tiny address space. No system that you know of has a tiny address space like this, but just for simplicity. And what it means is the page table for this process is going to have to store up to 8 translations, right? It's not too hard to imagine. It's just going to tell us for each of these pages where it is in physical memory. That's it. It's going to say, hey, this virtual page 0, it's in physical frame 10. This virtual page 1, it's in physical frame 11, whatever. So let's look at what that might look like. It's going to actually look very similar. So it's going to tell us for each virtual page what physical page it's going to, right? And I'm going to use VP for virtual page, or maybe virtual page number, and physical. Well, I'm going to be a little more precise here, sorry. It's going to translate the virtual page number to a physical frame number for each of the virtual pages. So that means our page table has to have for 0, 1, 2, 3, 4, 5, 6, 7, potentially a translation. So let's say, virtual page 0 is in physical frame 10, virtual page 1 is in physical frame 21, virtual page 7 is in physical frame, whatever, 100, doesn't matter. So that would mean these are, parts of our address space, they're valid, and they have a physical location for them. Now, what's nice about paging is that this middle piece, let's say we're not using that part of the address space. That's okay. We don't have to have a location for it. We just have to have something in our page table that pays attention to that whether it's in use or not. And so what we're going to add is essentially a column to this table that tells whether the page is valid or not, whether it should be a legal part of, can we legally address that part of our virtual address space? So for these two and this one, it's valid. And then you can see for the remaining pages here, which we're not using, we'll just say that those virtual pages are no longer aren't valid, and therefore there's no physical page that corresponds to holding them. So you can see this kind of naturally supports what you might call a sparse address space. Because we can have big holes in it. In fact, we have many different holes that are just marked invalid, and we don't have to use them. Simple as that. So our page table has translations, our virtual page number to physical page number, physical frame number, and then whether it's valid or not. It's going to have some other stuff in it too, but let's not worry about that for right now. Any questions about that? Okay. Now, we'll talk about a lot of different structures, but our first page table structure is just going to be what people call a linear page table, or what you would just call an array. So if you think about it, what I'm really going to do here is copy some piece of this. I'm going to copy this part. It's really an array, and it's going to look like this. It's going to have, each of these is an entry in this page table. In this terribly drawn page table. It's just an array of page table entries. And you notice inside the page table, there's a physical frame number and a valid bit, but we don't have the virtual page number in the structure itself. Why is that? How do we find a translation if we don't store the virtual page number in there? Yeah. It's just the index. Yeah, right. It's an array. So when we take the virtual page number, 0, 1, whatever, it's just an index. The virtual page number is an index into, here, let's say we're referring to page 6 or something like that. We're just indexing into it. So when you index into something, that means you just need to know, what do you need to know to do an index calculation, to calculate the address of a particular page table entry? You need to know the virtual page number. What else do you need to know? Yeah. You need to know the size of a page table entry, absolutely. And then what else do you need to know? You need to know one more thing to find this location. Kind of need to know where it begins, right? Is that what you're... Sorry. Well, the offset is, yeah, we'll get to that in a second. The offset will need to do the full translation. That's true. But what I'm saying is we need to know the beginning of where this page table is in memory. So the page table is some contiguous thing in memory. We need to know where it begins. We're going to then index into it to find where the entry is that we're interested in, and then we're going to use that in the translation, which we haven't quite talked about yet. And then we'll use the offset in a second. So we have this really simple structure. It's an array of page table entries of some size. They have a physical frame number in them. They have a valid bit. And now we have to figure out how to do a translation. So let's just go ahead and do that so that we can understand it and then understand some of the issues with it. So let's do a translation. And in this example, we had these 8 pages. We haven't said how big these pages are. Let's make them some size. Let's make them 1 kilobyte page size, just for a simple example. So we have an 8K virtual address space. We have 8 pages, each 1K in size. I'll copy this so we can look at it again down here. Let's go here. So if we have this kind of system, we can look at our virtual address. And our virtual address, we immediately know if we have an 8 kilobyte virtual address space, we know how many bits we need. For 1K, we would need 10 bits, and for 8 of those, we need 3 more bits. So we have a 13-bit virtual address. And what we know is the bottom 10 bits, that's that part we call the offset, that tells us which byte within a page we're interested in. And then the top 3 bits tell us the virtual page number, or VPN. And you can see why we need 3, because we need to go from 0 to 8, 0, 0, 0, 0, 0, 1, etc., up to 1, 1, 1. So 0 to 7, sorry, inclusive. So what happens during translation? Well, what's going to happen during translation, and this is going to introduce the second problem, is basically we're going to take the VPN, which is taken from these 3 bits. This is going to be done in the hardware. And you can think of this as being part of what the MMU would be doing. And we need to figure out for the given page, like which page table entry we're referring to, right? We have to find that page table entry somewhere in memory. So what we're going to need is we're going to need the base address of the page table. And simply what we're doing here is let's call the base address, I don't know, let's call it B. So B points to the beginning of this table, B. And we're going to add VPN times the size of a page table entry. I guess I'll make that another thing there, not that I needed it. And that's going to take this VPN and get us, let's say, the entry that we're interested in. That's how we do, that's just the math of indexing into an array. It's as simple as that. It's just, you can think of it as being multiplied by, of course you can do it with shifts and things like that, but it's fine. So we need this base address, B. Then what we're going to do, okay, so then you're going to load the page table entry from memory, extract the physical frame number. Remember, that's inside of this entry, right? The physical frame number might be, for example, this number here. We're simply going to extract that and then form the full physical address, which is the PFN concatenated to the offset. That's the full physical address. So we'll call that the PA, physical address, PA. That's what translation is in a paging system. We have a VPN, we need to turn it into a PFN, or a physical frame number. Uh, our virtual page number, oh, what was that? That's not the right thing. Uh, was I not No, I'm doing fine. Huh. What in the world did I do? Did it just disappear? Huh. That is odd. I will stop this.